Welcome! In today's session, we'll explore problem number 231, power of 2. This is a common interview question designed to test your understanding of bit manipulation and mathematical intuition. Let's dive in to understand the problem and its solutions. The problem power of 2 asks us to determine if a given integer is a power of 2. Mathematically, this means checking if there exists some integer x such that the number n can be expressed as 2 raised to the power of x, or n equals 2 to the power of x. For example, the number 1 is a power of 2 because 2 raised to the power of 0 equals 1. Similarly, 16 is a power of 2 because 2 raised to the power of 4 equals 16. However, 18 is not a power of 2 because there is no integer x that satisfies the equation 2 to the power of x equals 18. In this problem, your task is to implement a function that takes an integer n as input and returns a Boolean value, true if n is a power of 2, and false otherwise. Now, let's look at some examples to better understand the problem. In the first example, the input is n equals 1. The output is true because 1 is a power of 2. This is due to the fact that 2 raised to the power of 0 equals 1. In the second example, the input is n equals 16. The output for this input is true because 16 is a power of 2. Specifically, 2 raised to the power of 4 equals 16. In contrast, for the third example, the input is n equals 18. The output in this case is false, as there is no integer x that satisfies the equation 2 to the power of x equals 18. Therefore, 18 is not a power of 2. In another example, the input is n equals 0. The output is false because the value 0 cannot be expressed as 2 raised to any integer power. This is because 2 to the power of x is always greater than 0 for all integer values of x. Similarly, if the input is n equals minus 16, the output is also false. Negative numbers, such as minus 16, cannot be powers of 2 because 2 raised to any integer power is always positive. Finally, we need to consider the constraints and edge cases for this problem. The input n is a 32-bit signed integer that falls within the range of minus 2 to the power of 31 to 2 to the power of 31 minus 1. Edge cases include handling 0, negative numbers, very large values close to the limits of this range, and smaller powers of 2 like 1, 2, and 4. These edge cases ensure that our solution is robust and can handle all valid inputs correctly. To determine if a number is a power of 2, we considered multiple approaches, beginning with the brute force method of iterative division. The intuition here is straightforward: a power of 2 divides evenly by 2 until it reduces to 1. For instance, 8 divides to 4, then 2, and finally 1, without ever leaving a remainder. The steps involve checking if the number is less than or equal to 0, which immediately makes it invalid. Otherwise, we repeatedly divide it by 2, ensuring there's no remainder at any step. If we reach 1, the number is confirmed as a power of 2. This approach is simple, with a time complexity of O log n, due to the repeated divisions, and it requires no additional memory, giving it a space complexity of O 1. However, there are trade-offs to consider, which we'll explore next. The iterative division approach, while straightforward, has limitations. It involves multiple division operations, which can be less efficient compared to bitwise techniques. To address this, we explored an optimized approach using bitwise manipulation. Here, the intuition lies in the binary representation of powers of 2, they all have exactly one bit set to 1. For example, 1 is 0001, 2 is 0010, 4 is 0100, and so on. A key property of such numbers is that the bitwise n of the number in 1 less than itself is always 0. For instance, for 8, 1000, subtracting 1 gives 7, 0111, and there an operation results in 0. This leads us to a very efficient check: if the number is greater than 0 and this condition holds, it's a power of 2. The steps are simple: validate the number is positive, and then apply the bitwise operation. If true, the number qualifies. The bitwise manipulation approach is not only elegant but also highly efficient. Its time complexity is O1, since the bitwise operation is performed in constant time, and its space complexity remains O1, as no extra memory is required. This makes it a robust solution. However, it assumes familiarity with bitwise operations, which might not be immediately intuitive for everyone. Another method we explored is the mathematical approach using logarithms. Here, the idea is to calculate the base 2 logarithm of the number. If the result is an integer, the number is a power of 2. This utilizes the property that powers of 2 have whole number logarithms in base 2. The steps are straightforward: check if the number is positive, compute the logarithm, and verify if it's an integer. While this runs in constant time and space, there are some trade-offs to consider in terms of its precision. The logarithmic approach, while mathematically elegant, has its own limitations. It relies on floating point calculations, which can introduce inaccuracies for very large numbers. This makes it less reliable compared to bitwise operations. Additionally, it's computationally more expensive than bitwise checks, even though its overall complexity is still 1. After evaluating all these methods, the bitwise manipulation approach emerged as the most suitable choice. It combines efficiency, simplicity, and robustness. By leveraging the binary properties of powers of 2, it avoids the pitfalls of both iterative operations and floating point precision errors. This makes it not only the fastest but also the most reliable solution for this problem. To summarize the trade-offs, the iterative division approach, while simple, is slower due to its log n time complexity and repeated operations. The logarithmic check is elegant but prone to precision issues due to its reliance on floating point arithmetic. In contrast, the bitwise manipulation approach stands out as the most efficient, with constant time complexity, no precision concerns, and a direct reliance on the binary representation of numbers. This makes it the clear winner among the three methods, offering speed, accuracy, and minimal computational overhead. To determine if a number is a power of 2, we use a technique called the bitwise operation approach. This method is efficient because it directly leverages the properties of binary numbers. The first step is to understand the binary representation of powers of 2. A number is a power of 2 if it has exactly one bit set to 1 in its binary form. For instance, the number 2 in binary is represented as 10, 4 as 100, and 8 as 1000. Each of these examples has precisely one bit set to 1. Next, we use a clever bitwise trick to verify this property. If you take any power of 2, subtracting 1 will flip all the lower order bits, including the rightmost one. When you perform a bitwise an operation between the number and its value after subtracting 1, the result is always 0. For example, with n equals 4, its binary form is 100, and n1 is 011. The operation 100 and 011 clears the only set bit, resulting in 0. Similarly, for n equals 8, the binary form is 1000, and n1 is 0111. The n operation again yields 0. This property makes the method both elegant and computationally efficient. To make the algorithm robust, we need to account for edge cases. If n is less than or equal to 0, it cannot be a power of 2. This includes negative numbers and 0. Additionally, the number 1 is a special case. It is a power of 2 because it satisfies the condition that 1 and 1 to 1 equals 0. With edge cases in mind, we can write the algorithm in just a few steps. First, check if n is greater than 0. If it isn't, return false immediately. Next, compute n and n1. If the result is 0, return true, indicating that n is a power of 2, otherwise, return false. This approach is highly efficient, with a time complexity of 1, since it involves only a few bitwise operations. The clarity of this algorithm lies in its direct use of binary properties, making it intuitive for problems involving powers of 2. Furthermore, by checking n greater than 0 upfront, we ensure that invalid inputs like 0 or negative numbers are excluded right away. What makes this algorithm even more appealing is that it does not require any additional data structures. It operates directly on the integer n, using bitwise operations, which results in a space complexity of 1. The algorithm is not only memory efficient but also optimized for performance. One optimization is the early exit condition. By immediately returning false for n equals 0, we avoid unnecessary computations. Another advantage of this approach is that it eliminates the need for division or loops, which are commonly used in other methods. This makes it particularly well suited for environments with limited computational resources. Finally, the code implementation of this algorithm is remarkably concise. It consists of a simple function that first checks if n is positive and then applies the bitwise trick to determine if the result is 0. This combination of efficiency, simplicity, and clarity makes the algorithm a standout solution for the problem. Let's now walk through two examples to see the algorithm in action. First, consider the input n equals 16. Since 16 is positive, we move forward. The binary representation of 16 is 10,000. Subtracting 1 gives 15, which in binary is 01111. Performing the AND operation between 16 and 15 results in 0. Because the result is 0, the function returns true, confirming that 16 is a power of 2. Now, for the second example, let's take n equals 18. Again, 18 is positive, so we proceed. The binary representation of 18 is 10,010. Subtracting 1 gives 17, which in binary is 10,001. When we compute 18 and 17, the result is 10,000, which is non-zero. Since the result isn't 0, the function returns false, indicating that 18 is not a power of 2. These examples highlight the precision and reliability of the algorithm in determining whether a number is a power of 2. This implementation checks if a given integer n is a power of 2 by leveraging the properties of binary numbers and bitwise operations. Here's the step-by-step explanation. 1. Early return for non-positive numbers. The first condition checks if n is less than or equal to 0. Since powers of 2 are always positive integers, we immediately return false for any non-positive input. 2. Binary representation and bitwise check. A power of 2 has exactly one bit set to 1 in its binary representation. For example, 1 is 0001, 2 is 0010, 4 is 0100, and so on. The bitwise operation, n and n1, exploits this property. Subtracting 1 from a power of 2 flips all bits after the single 1 bit to 1 and the 1 bit itself to 0. Performing a bitwise AND, n and n1, results in 0 if and only if n is a power of 2. 3. Return the result. If n and n1 equals 0, the function returns true, indicating that n is a power of 2. Otherwise, it returns false for all other numbers. This approach is highly efficient, operating in constant time O(1), since the bitwise operations are performed in a fixed number of steps regardless of the size of n. The function is concise and handles all edge cases, including 0 and negative numbers, making it robust for any input within the problem's constraints. This is the Java implementation of LeetCode problem number 231, power of 2. The logic mirrors the Python implementation, leveraging the same bitwise operation to determine if a number is a power of 2. Specifically, the expression n and n1 equals 0 checks if the number has exactly one bit set in its binary representation. Key differences include Java's use of type declarations and its class-based structure. This implementation is concise and adheres to Java's conventions while maintaining the same functionality as the Python solution. To determine if a number is a power of 2, we start with the input n equals 8. First, we check if n is positive. Since n greater than 0, we can proceed to the next step. Now, we apply the bitwise operation n and n1 equals 0. This checks if there is exactly one 1 in the binary representation of n. The binary representation of 8 is 1000. Subtracting 1 from 8 gives 7, which in binary is 0111. When we perform the bitwise AND operation between 1000 and 0111, the result is 0000. This result equals 0, meaning the condition evaluates to true. Therefore, the function concludes that 8 is a power of 2 and returns true. Now, let's analyze the input n equals 10. As before, we start by checking if the number is positive. Since n greater than 0, we move forward. The binary representation of 10 is 1010. Subtracting 1 from 10 gives 9, which in binary is 1001. Performing the bitwise AND operation between 1010 and 1001 gives the result 1000. This result is not 0, so the condition n and n1 equals 0 evaluates to false. As a result, the function determines that 10 is not a power of 2 and returns false. For the input n equals 0, the process begins with the same initial check to see if n is positive. Since n is not greater than 0, the function immediately returns false without performing any further computations. This is because non-positive numbers cannot be powers of 2. From these examples, we can extract some key insights. First, the bitwise operation n and n1 = 0 is based on the fact that a power of 2 has exactly 1 in its binary representation, and subtracting 1 flips all the lower bits, resulting in an n operation that produces 0. Second, if n is less than or equal to 0, we avoid unnecessary calculations and directly return false. Finally, this approach is highly efficient, with a time complexity of O(1), as it involves only a fixed number of operations regardless of the size of the input. The time complexity of this solution is constant, or O(1), because the number of operations it performs does not depend on the input value of n. To break this down, the first step is a simple comparison to check if n is less than or equal to 0, which takes constant time. Next is the bitwise operation n and n1. This operation evaluates each bit of the binary representation of n. However, the number of bits is fixed, determined by the system's word size, like 32 or 64 bits, meaning this step is also O(1). Finally, the equality check to see if the result of the bitwise operation equals 0 is another constant time operation. When we combine all these steps, the total time complexity remains O(1), regardless of the size of n. The space complexity of this solution is also O(1), indicating it uses a constant amount of memory. The algorithm doesn't allocate any additional data structures or memory that grows with the size of n. Let's break it down. The input variable n is passed to the function but does not count as extra space, as it's provided by the caller. The bitwise operation n and n1 only uses temporary storage for the result, which is limited by the system's word size, such as 32 or 64 bits. Since no other memory is allocated during the execution, the algorithm operates within a fixed amount of space, leading to a space complexity of O(1). When we compare this approach to a naive method, the difference becomes clear. A brute force solution might repeatedly divide n by 2 until it reaches 1, checking if the remainder is 0 at each step. This would require O log n time because the number of division steps depends on the logarithm of n. However, the current solution is more efficient because it utilizes the binary representation of powers of 2, where only one bit is set to 1. By using the bitwise operation n and n1, we can determine if n is a power of 2 in constant time, O(1), without requiring iterative checks. This efficiency comes from the mathematical property of powers of 2 in binary. For example, subtracting 1 from a power of 2 flips all bits after the rightmost one, and performing n and n1 clears that bit, resulting in 0. This operation is constant time because it is bounded by the system's fixed word size. As a result, the current approach achieves both O(1) time and space complexity, making it far more optimal than the naive method. One common mistake when solving the power of 2 problem is forgetting to check if the input number is positive. Remember, powers of 2 are always positive integers, so failing to ensure n greater than 0 might lead to incorrect results. For instance, if -8 is passed as input, without this check, your code might mistakenly return true. A simple condition to verify that n is greater than 0 can prevent this. Another issue arises when floating point division is used instead of integer division. Performing n/2 instead of n/2 may introduce precision errors or make the logic unnecessarily complex. Using integer division, like n/2 in Python, ensures simplicity and accuracy. Lastly, it's easy to overlook edge cases. For example, n equals 1 is a valid power of 2, but some implementations might miss this. Testing for edge cases, including boundary values, helps ensure your solution handles all scenarios correctly. Another common pitfall is relying on unnecessary loops or recursion to solve the problem. While iterative division might work, it's less efficient than using a bitwise approach, which can solve the problem in constant time. A more optimal solution involves leveraging bitwise operators. However, misusing these operators is another frequent mistake. For example, the logic behind n and n1 == 0 is specific to powers of 2, but confusing it with something like n1 == n could lead to bugs. To avoid this, it's important to fully understand how these bitwise operations behave before applying them. This not only ensures correctness but also demonstrates a deeper grasp of the underlying principles. A key insight for this problem is recognizing the unique binary representation of powers of 2, they always have exactly one bit set. For example, the number 4 is represented in binary as 100, and 8 is 1000. This leads to an optimal solution, using the condition n greater than 0 and n1 equals 0. This works because subtracting 1 from a power of 2 flips all bits after its rightmost set bit, making the bitwise an operation result in 0. While iterative division is a valid approach, many interviewers prefer a bitwise solution as it's more efficient and demonstrates a deeper understanding of binary operations. It's also important to explain edge cases, such as handling n equals 0, negative values, or very large numbers, to show your solution is robust. Additionally, this problem is closely related to others, such as LeetCode 191, which involves counting the set bits in an integer, and LeetCode 326, which applies similar logic to powers of 3. Exploring these problems can strengthen your understanding of the underlying patterns. There are a few alternative approaches to consider. One is iterative division, where you repeatedly divide n by 2 and check if the remainder is ever non-zero. While this method is simple and intuitive, it has a time complexity of O log n, making it slower than bitwise solutions. Another approach involves using logarithms. Here, you calculate log 2, n, and check if the result is an integer. While this method is mathematically sound, it relies on floating point operations, which can introduce precision errors. A third option is pre-computation, where you store all the powers of 2 within the range of n and check if the input exists in this set. While this can be useful for specific scenarios, it is space-intensive and doesn't scale well for large ranges. Each of these methods has its trade-offs, and understanding when to use them is key to writing efficient and reliable code. Great job! We've covered how to determine if a number is a power of 2 using efficient algorithms. Remember to practice bit manipulation and mathematical properties, as they often appear in coding interviews. Thanks for tuning in, see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!